I'm going to talk about common developer crypto mistakes. The common part is, sort of subjective because it's basically based on my experience over the past 6 years as an information security engineer with 2 different companies, looking at approximately 200 different projects, varying from small to large, including vendor products. I apologize that most of actually all the examples are in Java. It's been since 2008 since I've done any .NET stuff, so I'm a little rusty on that, and I know the frameworks have changed a lot, and I didn't want to have to go and re-research that. So, anyways, this is the bio page that we're always supposed to put up. You really don't need to know anything about this except for basically an old fart. So, one of the things that I kind of get nervous every once in a while, especially when I speak to large crowds. So, I try to remember that advice that my mom told me about when you're going to speak in front of an audience, you imagine yourself talking in your underwear. Wait, that's not right. Imagine your audience speaking to them in their underwear. So I have a sort of a spin on that, basically, that, I try to imagine them, but so I don't ever want to see geeks in their underwear, okay? So you just don't want to see that. So I basically imagine them in their encrypted underwear. All right, so anyways, I'm going to basically talk a little bit about some, the points that I'm going to cover, some good news and some bad news, just start out with an overview and then basically talk about mistakes in random number generation, secure hashing, symmetric encryption, and asymmetric encryption. I usually prepare this talk for people who are in the security field, and most of them are aware of the terminology that I use. I will try to explain the terminology, but if I forget and somebody's confused, and I might not be able to see everybody's eyeballs if you have that deer in the headlight look. So if you basically want me to stop, give me a timeout sign or something and say, could you explain that? The miscellaneous topics, sometimes I talk fast, and if I do, then we'll get to these. It's not a big deal that would be in the slide presentation, and most of them are all self-explanatory anyways. So the good news and the bad news. The good news is we used to be telling the developers, number one thing, don't ever design your own crypto, right? That was, for 20 years, the number one message that we were trying to get through people's heads, right? And, well, I want to say that basically I think that message has been well received. It may be because of standardization, that people are required to use like FIPS 142 stuff or NIST compliant things or PCI DSS or something like that. Whatever the reason, I think we've been successful with that. I have not seen a case where development teams have invented their own crypto since 1997, so I'm pleased with that. The other message that we basically tell them is don't implement your own crypto because you're going to screw it up unless you know what things like side channel attacks are and memory leak attacks and stuff like that are. That's even a pretty rare occurrence because we've gotten a lot of now pretty solid crypto packages built into the standard frameworks. Okay, but there is still some bad news. One is that the developer expertise basically comes from copy and paste of Stack Exchange and other similar sites, and so they still get things wrong. In particular, there seems to be a big confusion between confidentiality and authenticity. The standard encryption can provide both, but you have to be careful of things like Cipher Modes and stuff like that, which I will touch on a little bit later. Confidentiality, basically, it prevents people from comprehending your plaintext data, right? Authenticity, or also known as data integrity, prevents somebody from, it allows you to detect intentional tampering with the data. And then there's confusion of cipher modes and padding schemes, which is kind of related to those other things about confidentiality and authenticity, and we'll jump onto here shortly. The other thing is that we still see occasionally some, where there's like legacy applications doing encryption, especially with back office stuff or mainframe applications and stuff like that. They're still using broken crypto, like DES or RC4 or something like that. And then the other bad news is, and I don't really know where to go with this. I mean, I don't really see a whole lot of hope, but even the experts are still getting things wrong. Example would be like PGP or GPG or other, and OpenSSL and other similar TLS suites. And so far this year, in 2016, does everybody know what a CVE is? Common Vulnerability Enumeration, that the National Vulnerability Database in NIST has? All right, so far, OpenSSL has issued 11 this year, 11 CVEs just so far this year for OpenSSL, right? Last year in 2015, there were 34. The year before that, there was 24, right? So these are people who basically have lots of crypto experience. In fact, I know several of them, but they're still screwing things up. So if they're screwing things up, it's kind of disconcerting, because most of us are not as good as those people. So random number generators. I'm sure you all know what random number generators are, but one of the things is that this basically, random number generation is sort of the key to where we get everything that we need to get solid cryptography. Poor randomness basically is going to imply you have broken crypto. And a simple example to think about is basically if you have key generation and you have a weak random number generator or a predictable random number generator, because some people use things like linear congruential random number generators or something like that with predictable seeds. You basically have predictable keys. So cryptographers demand cryptographically secure random number generators, or typically called CSRNGs. In Java, how many people here program in Java? Okay, it's about half. So in Java util random is not a CSRNG. It's a linear congruential random number generator. It has a very short period, around 2 to the 48th power. It's basically similar to if you ever use DRAND in C. It basically works on the same principle. Java secure random is a cryptographically secure random number generator. The other thing is that when you use a CSRNG, you have to have an unpredictable seed. The seed entropy, in other words, basically how many bits you're feeding it in to set the seed value, has to, should at least equal and should ideally exceed the internal state of the random number generator. So if you're going to generate something like 160 bits, then you better have 160 bits of entropy. All right, so what do you look for if you're basically doing cryptography and you want to make sure that you're secure in terms of how you're using your random number generators? Well, one thing, look for any place that you're using Java util random, for instance, for anything related to crypto, including keys, including initialization vectors. Everybody know what initialization vectors are? Okay, good. Nonces, et cetera, right? If you have, when you do seeding for the CSRNGs, you need to look to see if they have sufficient entropy. If you require n bits of randomness, then you need to start out with n bits of randomness. You can't automatically stretch like if you had to flip a coin, right, and on or off, you just can't stretch that into, n bits of randomness. Okay, now the good news is generally this is not a problem if, like, for instance, you're using Oracle and Sun and most other implementations of secure random, or like the SHA-1 PRNG, which is a specific cryptographically secure random number generator. The default constructor for secure random basically uses dev-urandom when it's available. But it could be a problem, like, for instance, if you need a lot of randomness at boot time, or you're on a system like, say, Windows or something, which doesn't have dev-urandom or dev-random devices. So here's an example of the correct way to do it. Let's see here. So you notice basically that you call generate seed, and then you basically seed it with the number of bytes that you need. And why they flip the bytes, but I'm doing this here with SHA-1, which is 160 bits. So divide it by 8, you get the number of bytes. For JDK 8 and later, there's also, instead of get instance, you can use get strong instance, which does a little bit of extra stuff to making sure, like, it fails if it can't, like, create stuff. It'll go and check to see if you have dev-urandom and all that stuff. Okay. In terms of hashing, if you're basically doing one-way hashing, irreversible hashing, one of the things you want to look for is completely broken message digests or secure hashes, like MD2, MD4, MD5. I don't see too much MD2 and MD4 usage anymore, but I see quite a bit of MD5 stuff, especially with password hashes. The other thing is that occasionally you'll see people trying to use things like CRCs, CRC32 and stuff like that, for like file integrity. That's okay as long as there's never a chance that somebody else can grab that file and put it up. But even then, a secure hash isn't going to really do magic too much there. The difference between the secure hash and the CRC is that CRCs basically are only going to find accidental bit rot, essentially, right? But a secure hash should find intentional tampering as long as somebody can't change both the file and the hash. If they can recompute the hash, then all bets are off. The other thing is you should try to avoid, especially in new code, mostly broken algorithms. Any hash, basically, if it has collisions if it has n bits, the best theoretical break of a perfect hash is 2 to the n over 2. All right, that's basically by something known as the birthday paradox. And if they have a breakage of a collision, somebody can force less than that, then basically, there's a problem. So I think it's somewhere like around in the 2 to the 70th range or 2 to the 69th or something like that for SHA-1. So it's considered broken. And the attacks basically, as Bruce Schneier says, the attacks only get better, they never get worse. So, it's not imminent danger right now today unless you're basically worried about nation states as your attack source, but it's definitely a good idea to move off of them. If you're also concerned about local attacks, in other words, basically internal threat sources, then you need to also worry about the timing comparison of hashes. If you're using things like, say, base 64 encoding hashes and then comparing them with string equals, or taking the byte arrays of the hashes and comparing them with array equals, that's a timing dependent thing. Those small timings basically can be detected, and you can use it to basically break things like hashes with say, passwords or stuff like that. Now, over the internet, this is not really a problem because the network lag and the network jitter basically far exceeds the comparisons of these methods. But the way that you really should be doing is using message digest dot is equal in Java, and that's okay after 1.6017 because they basically had it so that it was timing dependent. It was basically just just doing a byte array comparison through all the bytes. In the other talks that I give to security people, I basically show how to do a timing independent comparison, but I'm not going to jump into that detail here. The other thing is that, assuming that you're interested in security beyond basically just confidentiality and stuff, if you consider like denial of service things, basically don't call things like message digest or update with unbounded input. Make sure that you check, because if you let an adversary basically define the input, then they basically can do denial of service attacks. Like, feed you 10 terabyte files or something. All right, misusing, the other common mistake that I see is misusing hashes, secure hashes, when you really need a message authentication code. A message authentication code basically ensures integrity because it's a keyed hash, and the key is basically only known to maybe certain shared parties that basically have to calculate the hash and to verify the hash, right? And that secret key is usually shared out of band. One of the things that sometimes people do is they just try to take like a message digest and like have a key and concatenate it with a message, and then say you use the message digest that way, like they'll call message digest dot update with the key concatenated with the message or something. You don't want to do that. There's a thing called a length extension attack that's vulnerable to. In Java, there's actually a class called Mac, and that's really what you want to use. That's basically implements a HMAC from the RFC 2104, and the proper way to do it is the way that's shown here, and where key at the bottom is like a secret key. Misusing a secure hash to mask data where the enumeration of all or most of the input space is feasible is also a big error that I see. Typically, like one of the things that I see is people say, well, I'm not allowed to put in, say, social security numbers, common like where I work at a bank, or they have some other kind of account number or something like that. And so they basically decide that they're going to hash the account number and put it into a log. Well, the problem is some internal attacker can get to the log. Well, if I can enumerate through all the hash values of all, 10 billion or something like that, I don't know what it is, but 10 to the 9 digits, 10 to the 10th, possible things, which is not hard to do, calculate all those, then I basically can compare those to the hash values in the log file. Same thing if you put it in as a key in a database, although presumably the database may be a little bit more protected than the log file. All right, so you just basically have to be conscious of whether your potential adversary can observe the actual hashes or not. If they can, and they can then pre-calculate all those possible values. So I mean, if you're having something like I don't know, let's say like first name, last name, street, and social security number, that's probably enough, entropy that somebody's not going to put all those things together. You could hash all that together and put it in a log file, but just doing something small like an account number or a social security number is going to get you into trouble. So, question is, can we ever use MD5? That comes up a lot because I see people using MD5 quite a bit. Well, the best collision attack against it is now I mentioned basically, theoretically, it would be 2 to the 64th, because it's 128 bits. You can see that it's substantially below that. It takes about 5 or 6 seconds now to force a collision on MD5 on just a regular laptop. All right. However, it's okay if you basically, in some cases, when you want to basically use a pseudo-random with it as a pseudo-random number generator, to like generate things like initialization vectors for symmetric ciphers in CBC mode. I would not recommend using it for any other mode for an IV, because, well, you'll see here coming up. The other thing is if you use it as an HMAC construct, so you're using, say, HMAC MD5, it's perfectly fine there. These 3 people that I'm not going to try to make a fool of myself and pronounce their names, because I'll probably botch them, basically proved that the HMAC security only requires that the underlying hash basically acts as a pseudo-random function. It didn't have to be collision resistant. So the fact is that there's collision attacks now known to MD5 basically doesn't really affect it as in the construct of an HMAC. And if you look at the RFC, you'll see basically the HMAC construction is such that basically it does a double invocation essentially of the underlying message digest, and the second one basically XORs it with some pad values. All right. So symmetric encryption weaknesses. Everybody's gotten rid of RC4, I hope, right? Obviously, if you're using key sizes too small, that's a problem. The one thing I guess that I would say to be aware of is that in Java, because they had the export regulations, right, there's 2 versions of triple DES. There's a 3-key triple DES and 2-key triple DES. And if you're using the 2-key triple DES, which you might not be aware of, that would be 112 bits effective key size. That was because the export regulations prevented it. So if you do not have the JCE unlimited strength jurisdiction policy files installed on your JDK, then you get the 2-key and it doesn't tell you. And then other things is basically people have used ASCII for keys, ASCII values. There's some various IV abuses that I'm going to show you kind of a cool demonstration of. And assuming, again, confidentiality applies, data integrity. All right, so ASCII keys, I mean, you see this a lot in code. Sometimes this part will be in a configuration file instead. More typically, it's just harder to illustrate it, but it's like, so you basically, if you see something like it says, get bytes or whatever, you know it's a problem. And the problem is that when you're doing this, right, you can use dictionary attacks, offline dictionary attacks to try to guess the key, just like you would with a password. Okay, anybody know what happens, what cipher mode you get when you do this? Right. Until recently, all the static analysis tools, probably recently was relative, I guess, but I would say till at least 5 years ago, for some reason they would flag the use of ECB if you like specified it as say AES / ECB / PKCS5 padding, but if you specified just AES, they weren't flagging that. They finally started to a couple years ago when people started complaining, like, don't you morons understand that these are the same things? So, but basically there's block modes and stream modes of block ciphers. There's also things like stream ciphers, of which I'm not talking about here, right? Stream ciphers are things like RC4, Salsa 20, which is Dan Bernstein's relatively new algorithm, and let's see, the be A5/1 and A5/2, which is used in GSM to encrypt the signal between your cell phone and a tower. But what we're talking about here, streaming modes, is basically things like OFB or CFB, cipher feedback mode, output feedback mode. Pretty much anything that's not ECB or CBC is a streaming mode. The key with streaming mode is you must never, ever, ever, ever reuse the same key and IV pair. All right, so you want to make sure that, and this includes basically like when you restart things. So like if you're seeding things with like say a constant seed and a random number generator for just even collecting or generating IVs, and you have a fixed key, and then like you restart your application and it goes back and recycles those IVs, you just screwed yourself. Streaming modes too also do not require any kind of padding. And then, all right, so one of the things is, you know, everybody knows by now that ECB is bad. It's one of the most commonly misused things because, first of all, it's the default mode, like I showed. Second of all, it's the first and usually sometimes the only example in textbooks. It's easy to implement because you don't have to worry about those messy, pesky IVs and what to do with them and stuff like that, and how to get them over to the other person and all these other things. And of course, if you actually have to transmit an IV, that makes your, you know, your little tiny social security number that you're encrypting, you know, the encrypted ciphertext is that much longer. So the weaknesses is basically that the same plaintext block always encrypts to the same ciphertext block, and that makes block replay attacks possible. So this is the other good example of seeing the patterns. Here you can see this slight image of Tux the penguin in the middle picture. With any other cipher mode, it looks basically completely random. All right, so what is a block replay attack? Well, basically, if you look at this, you see basically that the blocks in ECB are encrypted independently, right? So what that allows is basically the adversary can sort of mix up those blocks in any way that they want, and they can mangle them. You know, they can do things like remove them, they can duplicate them, they can mix them up. Basically, whatever they do, I mean, sometimes if they know what the structure of the message is, they can basically usurp the meaning of it. This example is from Bruce Schneier's Applied Cryptography book, which at one point in time was sort of considered required reading if you were interested in crypto at all. But basically, if you assume like a 8-byte block size, like DES or triple DES, and you had a money transfer system that you wanted to move dollars between banks, and you assume basically that the message format was something like this, then basically if you had this man-in-the-middle attacker, Mallory, and she was listening to the communication channel between the bank of Alice and the bank of Bob, because they always use Bob and Alice for everything in crypto, right? And she sets up accounts in both of them, and then she transfers some fixed amount of seed money to the bank of Bob and records the transactions, and then it goes back later and she's observing this man-in-the-middle channel and looking for the identical blocks. And eventually she isolates the transfer authorization codes or the numbers and stuff, and then she can now take her messages and insert her blocks into that communication channel and replace them, and with that fixed amount and her account number. All right, so the two banks are eventually obviously going to notice this, you know, maybe at the end of the day or whenever they reconcile accounts, but, you know, hopefully, but, you know, probably by that time, Mallory's already skipped town, so this is something that cannot be defeated by simply like prepending a date and time stamp to the bank authorization, because Mallory can replay individual blocks that lie on whole block boundaries. Right? In this case, it was like the depositor name and account number. Right? You can defeat it by like putting an HMAC or something like that to hash the entire message, or you can use another cipher mode that basically guarantees data integrity as well, like an authenticated encryption mode. All right, so you know, basically looking at any of these two things, there's also one of the key things is that ECB is the only cipher mode that does not use an initialization vector. right? So in Java, you basically look for the absence of either cipher.getIV or the IV parameter spec. You can check like the length of the resulting encryption, because usually the typical case is that the IV is prepended to the ciphertext and sent over with it, because the IV does not have to be kept secret. That's actually a misconception, and one of the reasons why people end up just seemingly use fixed initialization vectors, which is bad, or they determine them algorithmically, like, you know, by a counter or some other strange way. So is it ever okay to use? Well, technically, yes, when you got all these conditions satisfied. The real only time that I would ever recommend using it, and the only time that's actually correct to use ECB, is if you're using it with an asymmetric encryption algorithm, let's say RSA or El-Gamal or something like that. In those cases with asymmetric encryption, it's really the only proper cipher mode to use. So I'm not going to go through all the details here, but yeah, these slides will be available. Use of if the use of ECB seems okay, make sure that it's not in a scenario where somebody can replay it. Like for instance, if you're sending it over an SSL channel or something like that, you might be okay. But you could also ask yourself if multiple blocks of ciphertext are encrypted with ECB, and does the adversary have exposure to those, and will reordering be detected in any manner? And if your answer to yes is to those questions, if your answer is yes to all those questions, then you have a block replay and you shouldn't be using it. All right, so the other thing I mentioned is basically never, ever, ever, ever use a key IV pair in streaming mode, all right? Well, given an IV pair for the same, a key and an IV for the same cipher, basically we have a cipher bit stream, right? The way that a stream cipher works is essentially it generates a bit stream based on the key and initialization vector. And then basically that bit stream then gets XOR'd with the plaintext message, right? So, and pretty much every cipher in streaming mode works this way, and including stream ciphers. So that means basically that you have the encryption. The encryption basically is equivalent to this. All right, so let's see what happens when we encrypt two different plain text messages with the same key and IV. Well, what we end up with is essentially that if an adversary intercepts both of those ciphertext results, they can compute the XOR of both of those. By computing the XOR of both of those, what it ends up with is basically being the XOR of the plain text. Well, what do we do with the XOR of the plain text message? If they're like written in some kind of normal, you know, English language or some other kind of human language, they're going to have patterns in them. Or if there's like a character set that you write in, like ASCII or EBCDIC or whatever. Anybody still use EBCDIC? I mean, but so you basically you make a guess, you use frequency distribution based on the anticipated language or an anticipated format, you know, whether it's a credit card number or social security number or whatever, and you make a guess, and then you, based on the frequency distribution, you basically can determine whether the guess was likely to be right or not. If you have a modest-sized message, let's say a couple hundred characters, most of the modern computers, including your laptops, can basically crack this in a few minutes. All right. The more ciphertext that you create using the same key IV pair and observed by the adversary, the better. Now, does everybody remember WEP, that first abysmal thing? This is exactly what the problem was in this case, right? They basically recycled the IVs and stuff when the machine went down, and there was a lot of other problems too. But basically, it was a reuse of the same key IV pair was a major weakness there. If you have fixed message structures or things that they know that they're encrypting, it's even more trivial. All right, so here's an example that I found from Dr. Rick Smith And basically, he's taken some images here, right? So he's basically saying send cache, and he has an encryption key, and you get the send key encrypted. And this, these little corners here, these are just like a part of this exploded so that you can sort of see that it really is random. Or at least looks humanly random anyways, right? Right. So to recover the original image, we basically XOR the send cache with the encryption key. So we take the encrypted version and we XOR it again with the encryption key and we get send cache out. Cool. So let's try it with two different messages, send cache and a smiley face. Same encryption key, same IV. You get these two different versions of encrypted messages. And now we're going to XOR those together. Anybody see a problem? Okay, don't do that. But wait, there's more. It gets worse. An application that's doing this can actually allow a adversary to not only decrypt a message, if they can do a man-in-the-middle attack, they can actually alter the cipher text. This is from a Wikipedia example under the stream cipher attack. Basically where they're talking about, so this red part is the part that the man-in-the-middle attacker, Mallory, she's inserting this, basically, and this is the case where she's inserting something and basically it works out to the fact that she's changing the amount here, right? So this is a simple example, and you can read about it on Wikipedia. So authentication, authenticated encryption, I mentioned that a few times. What is it? Well, first of all, encryption by itself generally does not provide provides confidentiality, but not data integrity, aka authenticity, right? There's a couple approaches to authenticate encryption. One is called Encrypted Mac, where you basically take the message authentication codes that we talked about. Usually they use HMACs, and they basically apply the HMAC over the IV and ciphertext and then append the MAC to the end. And then when you decrypt it, you just do it the reverse. You calculate the MAC and you compare that to the MAC that was appended. And if they don't compare, then you don't do the decryption at all. Right? Then there's encrypt and MAC, where you encrypt the plaintext and append the MAC of the plaintext, and then do the reverse for the decryption. And then MAC, then encrypt, where you append the MAC of the plaintext, and you encrypt both of those together. And then the decryption is the opposite operation. The encrypt then MAC is the only one that's been provably secure against all known cryptographic attacks. Okay, it's built in automatically to some things like CCM, GCM, AEX, and other modes. The first two, CCM and GCM, are the ones that I recommend because those have been NIST approved, and those are the ones basically that your company's probably going to let you use. The other ones, some of them, like I think AEX, had patent restrictions on it. It's actually a little bit better, but I think it's still patented for another couple of years. Okay, so if you're going to, the other thing you can do is you can do your own, apply your own MAC. If you're going to do that, it's important to remember something called the Horton Principle that David Wagner, cryptographers David Wagner and Bruce Schneier came up with in a paper they wrote. And he basically said, it has to do with what do we have to apply the message authentication code to. So you basically want to do semantic authentication. We want to say, authenticate what we mean, not what we say. And that's where the Horton here's a who thing, that's where that came from, I guess. Basically, you want to avoid unauthenticated data that's included with the message. So either don't send on it, or either don't send it to start with, or don't rely on it, or include it in the MAC. Those are your only options. If you're going to send it, an example would be like you're concatenating metadata with an IV and the ciphertext in the MAC. If the metadata is something like a version of how I've implemented things, and you're not including that in the MAC, right? Then one of the things is somebody can take that or that version number and reduce the version number, and now basically they may be able to go back, like the example would be, I tell you that I'm using TLS 1.2, but I could change it to TLS 1.0 and then use the attacks that are in TLS 1.0 because basically we have a fallback attack there, right? Or it might be a message that says, the metadata might be something that says, this is from Alice or whatever, right? So those are things that basically you want to include those in the Mac. So overall, CBC is basically probably the most robust mode when used correctly. That means basically, I mean, the worst case scenario is that if CBC fails, it fails in a mode that's very similar to ECB, okay? So it's not total breakage, like the thing with the stream ciphers and reusing the same key IV pairs, that's total breakage. So you use it on a random key and a random IV and padding, or and then you put like an HMAC, you use the Encrypted Mac approach, and you're pretty good. The common mistakes that we've seen are basically people use a fixed IV or predictable IV, like a counter or something based on time or something like that. Or they fail to apply the Mac correctly. They use like encrypt and Mac, or Mac then encrypt instead of encrypt then Mac, or Big Mac, I don't know. So why do we need authenticated encryption? Well, the authenticity is when the ciphertext authenticity is in doubt, there's allows certain cryptographic attacks that are possible that either can divulge portions of the plain text or whatever. I don't know, how many here have heard of the padding oracle attacks? Not too many. All right. Back when, let's see, this was with IPsec, it was first discovered, Serge Vondenay, basically in 2002, basically said, hey, we have this attack. He talked about it in IPsec, and it was in an SSL. In IPsec, I think it was in the IKE part. It was dismissed as impractical until two researchers, Phil Rizzo and Tai Duong, basically did some research, put out some software called Poet, which was kind of like just made it an out-of-the-box attack thing, and then they attacked things like Java server faces and the ASP.NET, what was that? Help me, Bill. Where did he go? View state, thank you. So basically it allowed them to break those things and forge them. All right, so symmetric encryption weakness. All right, it's only true if you're using assuming confidentiality implies data integrity is wrong. That's true if you're using an authenticated cipher mode, like CCM or GCM, which are the two NIST ones, or you've properly done an encrypted Mac approach. If it's not required, if confidentiality is not required, then it's better and it's faster just to use an HMAC. That will ensure data integrity, but it doesn't actually provide confidentiality. But it does run a heck of a lot faster. So look for cases where plaintext is already known to the attacker and encryption is used to prevent tampering. And when I think plaintext being known, it's not necessarily that you know the exact plaintext for all the messages, but they may know like the format. For instance, on an SSL encrypting an HTTP request, right? The format of the message is going to start with get and some URL, and then HTTP/1.1 or whatever, right? And then maybe there's cookie headers and stuff like that. That's going to give the attacker enough known plain text to work with. Excuse me. We're doing on time. Okay, for asymmetric, there's a thing called chosen plain text attack. A chosen plain text attack is basically an attack where an attacker can basically choose whatever plain text that they want and encrypt it and then observe the ciphertext. So that could happen, like for instance, if you have a service that they can send in, an encryption service where you can send in encrypted text and it's not coming back over SSL and they can see it, that would be one example. But when you have an asymmetric cipher, it's always possible. And the reason it's always possible is because for asymmetric ciphers, you encrypt with the public key, you decrypt with the private key. The public key is assumed to be public, right? So so because of that, somebody can always do a chosen plain text attack. Well, how does that get you into trouble? Well, normally it's not a problem because we're encrypting highly unpredictable things like, session keys, temporary session keys, or cryptographic hash values and things like that, little short random things that we want to hide temporarily from an adversary. It does become a problem when we're trying to encrypt highly regular things that are short enough to enumerate all possible values, right? So like, an example, this is a real life example. I'm not going to say where I saw it, but it was in some vendor software. The application was using RSA algorithm to encrypt credit card numbers and store them in a database. And the problem is that if an insider there, like a DBA or somebody else that had access to that database could dump that database, they could also take that public key and generate all the possible credit card numbers. Now, it would take them a while to do that, but once they did that, basically they can compare them to the encrypted value in a database, and because of the chosen plain text attack, they could figure out which ones corresponded to what records. Okay, so key management problems. First thing is PCI DSS basically says that you have to change keys, crypto keys, at least yearly. All right, is that enough? Well, it may be, it may not be. Depends on how much stuff you go through. You got, for triple DES, and well, I'm assuming you're not using DES, but it'd be the same for any 64-bit cipher, like Blowfish would be an example too. You basically have 2 to 32nd times the 64-bit blocks of plain text. So in AES, it's pretty big, and you're not going to probably reach that limit, but that's just something to keep in mind, right? So you might want to keep a counter, for instance, of how much plain text you've actually encrypted, and so that you can sort of use that to trigger a rekeying thing sort of in advance, right? So that instead of just doing it by a time period, you're doing it based on how much you actually encrypt. Where you store your keys? Well, ideally, you want to store it in a hardware security module or a trusted platform module, but that's not usually something that most development teams can do because, those things cost money and stuff like that. TPMs usually are only on like laptops. HSMs are on, available from servers, but they cost money for licensing. So the one thing that I see is pretty common, and most of the static analysis tools basically will flag, is you see hard-coded keys put in a source code or put in the properties files. Right? The problem with that is that, generally you as developers keep your stuff in version control somewhere on Git or Subversion or CVS or whatever you're using, source safe, right? Have you ever looked to see how many people actually have access to your source code, right? If you throw your encryption keys in there, yeah, they have access too. Everybody that has access to your version control, right? So the one thing that's sort of okay to do is if you put them in a config file, you lock down the config file, and that config file, that encryption key is picked by the operations staff, and it's unavailable to everybody else. So you don't put it in a version control system. You don't make it available to all the dev teams and stuff like that. A better solution is using something like, for instance, if you're on .NET, to use the data protection API. It's great. It basically, you can tie that into IIS. It'll drive it right off of the password. It stores it in the registry. It requires, special level access to get at. it's very secure. I really wish that Linux things had something more convenient like that. I mean, they do have some stuff with like GPG and stuff, but they're very difficult to use. The other option might be like if you're using WebLogic, Oracle WebLogic has a thing called WebLogic encryption services, right? And then a third possibility is put it in a Java key store, put a password on the private keys, and in the key store for its integrity, so somebody can't replace the private key. Don't ever put the encryption. The other thing is, the other point I would like to make is don't ever put the encryption key in the same file with the data that's going to be encrypted. So many times I see an encryption key in with a encrypted database password, for instance, right? That's kind of just defeating the purpose. It's like, at least make it hard on the attacker that they have to steal multiple files, for crying out loud, right? Okay, encrypting data in a database. There's three ways to basically do this. One is to have the database engine itself do it via transparent data encryption. Another is basically use like a proxy, something like MIT's CryptDB, and another one is basically do it with your own application code. From the application perspective, I see quite a bit of places choosing the TDE approach because it's the simplest. It basically is transparent to the application. Okay, they lied. It's almost transparent. There's some things that you can't do. You can't do like range searches. You can't do things like matching, you know, say this is like this. And you can only use B-tree indexing. You can't use bitmap indexing. Of course, I don't think there's probably anybody going to be encrypting things like, you know, true false values and stuff anyway, so it probably don't matter. But it is available for both Oracle and Microsoft SQL Server, and it probably, and I'm not an attorney here, so I'm not going to speak like one, but it probably, I think, probably satisfies the letter of the law for the PCI DSS compliance. But I'll tell you one thing, if I was a PCI auditor and I saw somebody do this, I would fail you, because I don't think that it follows the spirit of the law, right? It basically offers encryption at a column, table, and table space levels, and it has usually a limited number of ciphers that it supports, you know, typically like AES and triple DES. The way that it manages keys is there's like master key that acts as the key encryption key, and that key is used to basically encrypt the individual keys for the tables or the columns or the table spaces. Usually they use CBC mode, but they use the same IV for all the encryptions. Well, why would they do that? That sounds stupid, right? We just talked about using different IVs and stuff. Well, for one thing, is if you want to be able to index stuff that you're going to encrypt, right? Somebody puts in a credit card number, and you encrypt that credit card number, and if you use a random IV each time, it encrypts the different ciphertext each time. It makes it a little tough to index, right? So that's why they basically use the same IV. Now they will support a thing like, at least in Oracle, I checked this out for the SQL Server, but they have a SALT thing that allows a non-deterministic encryption that essentially under the hood is basically generating random IVs. You want to use a SALT. But the question is, why does this fail? Well, what is your threat model? Basically, any application that has the database table or the column open, then any other application that has access to that table has access to the encrypted data, right? That's not a problem, basically, if the data is properly partitioned and you use database views. But most of the applications that I see, they're a little bit lazy. They don't do that. So the other thing is that backups, depending on how the backups are done on the database, could end up actually dumping the stuff in plain text. So usually the data that we're encrypting in a database is less than 20 bytes and has a particular format and limited possible value. So when you're using like the same initialization vector, even with CBC mode, right? I said basically it sort of fails to like ECB mode. Well, then basically you have patterns that pop out, and they can allow an attacker, an adversary that has access to the database, even if they have after just seeing the encrypted values, they basically can enumerate those patterns. Really, essentially what the whole point of why TDE was done, and the only attack, as far as I'm concerned, that it actually protects is basically somebody comes into your server room and does a smash and grab of your hard drive, right? So they basically have that hard drive now, and it's now offline, and they don't have that master database, key encryption key that basically allows them to encrypt the stuff in the tables. But for online access, it's basically total failure. So, how are we on time here? 5 minutes for a talk or 5 minutes for including question and answer? Total. Okay, so I'm going to stop here and field any questions and stuff. Yes, Mr. Google.
So my question is, what do you recommend in the instance where you do need to be able to query the database with using like or do like string, like partial string searches? Is like the drive encryption pretty much the only way to
Well,
file system?
okay, so the question, and correct me if I'm wrong, the question is basically says, what do you use for encryption in a database if you have to do like comparisons or range comparisons and stuff like that? Is that essentially your question? Okay. Unfortunately, the only way that you're going to get around this is basically to be able to re-architect your database and do this with application level encryption. So like for instance, let's say that you want to have a thing where you want to have a comparison of the last 4 digits of the credit card number. What you do, you store those. First of all, I mean, last 4 digits of credit card numbers and stuff like that can be stored in plain text. So you just put them in plain text and you use that for that comparison piece. If you have to do it arbitrarily, I think you're pretty much screwed. Unless you basically can afford to do non-index searches. And, we all know that's not really going to fly unless you have a really small number of records. I mean, if your records set was, something where a brute force search in the database would work, then sure, you can do that. But TDE is not going to fly. You might want to look at CryptDB. It's got some interesting technology. It does have some, some people would say major performance hits, even on stuff that you're not encrypting, but yeah, that's about the best you're going to do. Anybody else have a question? You in the first row of the second section there.
So you're talking about the chosen plaintext attacks for, but did you mention the solution to that? Like if you've got a small set of data, like a social security number, do you append random data to the end? How do you resolve those sort of things?
Well, the way you generally fix that is basically you use a random IV and you don't use asymmetric encryption. Right? So, and you're doing it in an application level. But it goes back to, like, if you're putting it in a database, how do you search it indexed? I mean, that's the catch-22, right? There is not really a good solution for that. But generally, asymmetric encryption was pretty much intended for key exchange operations. Like, for instance, I don't want to have to be able, if I had to encrypt with everybody out here in the audience, it's a lot easier for them to just say, publish your public key somewhere in LDAP or wherever, right? And then I go and I look it up, and then I encrypt something. I take a session key, right, and I encrypt using asymmetric encryption, I encrypt that symmetric key with the asymmetric encryption, and then I use that key, the symmetric encryption, like AES or whatever, to actually encrypt a message, and then I send you that and the encrypted session key. Right? That's the way it was intended to work. Somebody else had their hand up back. Yeah, you.
So what do you recommend for wanting to hash a password value or store a password value in a database?
Okay, so the question was, what do you recommend for storing and hashing a password in a database? Well, there are things that are specifically designed for this. Probably the best one that I've seen is called Scrypt. Letter S, crypt. There's one called bcrypt, which is based on Blowfish. Blowfish is kind of it has a key setup that's really, really slow. When you do that, if you're going to do these, there's also another one called PBK, yes, thank you, PBKDF2, password-based key derivation function, version 2. All those things basically will work. The key is basically you make it the number of repetitions enough, like I would say, like at Wells Fargo, for instance, we allow any of those types of methods, or even just like a SHA-256 hash, but you have to do at least 10,000 repetitions, and you have to have a random 64-bit salt. Okay, so anybody else? The lights are being turned down. I guess it's time to take a nap. No one else? Okay, well, thanks for attending. Enjoy your lunch.